Uranus looks so calm in photographs that its real strangeness is easy to miss. It looks calm. A pale blue-green disk, almost smooth, almost empty, almost polite. No great red storm like Jupiter. No golden rings like Saturn. No wild dark vortex like Neptune. Just a soft frozen sphere, far from the sun, turning quietly in the outer dark. But that calm face is the misleading part. Beneath it is a world lying almost sideways, with one pole staring at the sun for decades, while the other waits in darkness for half a human lifetime. Around it, moons and rings follow that impossible tilt, as if the entire system has been knocked over and then taught to pretend this was normal. Inside it, heat that should still be escaping after the planet's violent birth appears strangely muted, not absent as once thought, but far weaker than its near twin Neptune. And wrapped around it is a magnetic field so badly misaligned and off-center that it does not behave like the field of a well-organized planet. It tumbles through space like a lantern hung from the wrong point. For decades, the easy story was that Uranus broke the rules. But the deeper and more uncomfortable argument is different. Uranus may not be breaking planetary physics at all. It may be exposing the fact that the rules we wrote were too narrow, built from Jupiter and Saturn, then carelessly extended to a class of planets we barely understand. The seventh planet is not an exception at the edge of the solar system. It may be our closest key to the most common kind of planet in the galaxy. That is the debate. Is Uranus a freak accident, a world damaged by one ancient catastrophe? Or is it a warning that ice giants, sub-Neptunes, and volatile-rich planets follow a more complicated physics than the solar system first taught us? The strongest counter-argument is serious. We have only one close spacecraft encounter with Uranus. Voyager 2 flew past it in 1986 and gave us a few hours of close-range data. Since then, telescopes have improved the picture, and some old claims have softened. Uranus is not literally heatless. Its atmosphere is not literally dead. Its magnetic field, while strange, may be part of a broader ice giant pattern because Neptune is magnetically strange too. A careful scientist should not turn one flyby and a few dramatic numbers into a final verdict. But that caution does not make the mystery smaller. It makes it sharper, because if Uranus is not simply broken, then the problem is bigger than one tilted planet. The problem is our model of how planets form: cool, convect, magnetize, and age when they are built mostly not from rock or gas, but from water, ammonia, methane, hydrogen, helium, pressure, and time. To understand why Uranus matters, we have to begin with the rulebook it seems to violate. Not a rulebook written by people, but one written by a rotating disk of gas and dust more than 4.5 billion years ago. The solar system began as a collapsing molecular cloud. It was not still. Nothing in the galaxy is truly still. The cloud had a slight rotation, and as gravity pulled it inward, conservation of angular momentum made that rotation faster. A huge diffuse cloud contracted into a young sun surrounded by a flattened disk. In that disk, grains of dust and ice collided, stuck, broke, merged again, and eventually formed the bodies that would become planets. The disk mattered because it gave the young solar system a common direction. Nearly everything orbited the same way because nearly everything formed inside the same rotating sheet. The planets did not assemble from random directions like stones thrown into a bag. They assembled inside a shared flow. The first expectation follows from that. Planets should orbit in the same direction, and unless later events disturb them, they should spin with axes not too far from upright relative to the disk. Jupiter follows this expectation almost perfectly. Its axial tilt is only about 3 degrees. It spins rapidly, once in less than 10 hours, but its axis is nearly upright. Saturn is tilted more, about 27 degrees, but still in a range that planetary dynamics can explain with long-term resonances. Earth is tilted by about 23.5 degrees, enough to give seasons, but not enough to make the planet feel overturned. Mars is similar. These worlds lean. Uranus does not lean. Uranus lies down. Its axial tilt is about 98 degrees. In simple language, its rotation axis is almost in the plane of its orbit. If Earth behaved this way, one pole would point almost directly at the Sun during part of the year, while the other pole would disappear into decades of night. On Uranus, that geometry is real. The planet takes about 84 Earth years to orbit the Sun, so each pole can spend roughly 42 years in alternating light and darkness. A world this tilted should be a theater of extreme seasons. The second expectation concerns magnetic fields. A planet generates a large magnetic field only if it has electrically conducting material moving inside it. Earth uses liquid iron in its outer core. Jupiter uses metallic hydrogen deep in its interior. The motion of conducting fluid, organized by rotation, works as a dynamo. Because rotation helps organize the flow, the magnetic field usually stays roughly related to the rotation axis. It does not have to align perfectly. Earth's magnetic axis wanders and tilts. Jupiter's is tilted, but the basic pattern should not be completely chaotic. Uranus again refuses the simple picture. Its magnetic axis is tilted by nearly 60 degrees from its rotation axis, and the magnetic field is also offset from the planet's center by about 1/3 of Uranus's radius. That is not a small adjustment. That means the magnetic field is not coming from a neat, deep, central dynamo like the one we imagine inside Jupiter. It looks as if the planet's magnetic engine is located in an off-center shell, not in a symmetrical core. The third expectation is thermal. Giant planets form hot. During formation, material falls into a growing planet's gravity well, and gravitational energy becomes heat. A giant planet is not a cold ball assembled gently. It is a pressure cooker created by collapse. After formation, that stored heat should leak outward for billions of years. Jupiter emits more energy than it receives from the Sun. Saturn does too. Neptune, though much farther out, emits more than twice the energy it absorbs from sunlight. For a long time, Uranus seemed almost silent in this respect. Voyager-era estimates suggested that Uranus emitted roughly the same amount of energy it received, as if the planet had somehow lost or hidden nearly all of its primordial warmth. More recent analyses have complicated that old picture. Uranus does appear to generate some internal heat, perhaps around 15% more energy than it receives from the Sun. But the anomaly remains because that is still far below Neptune, which is only modestly more massive and belongs to the same broad planetary family. So the corrected version is not that Uranus is dead inside, it is that Uranus is strangely quiet. It is not thermally silent, but thermally muted. And in science, that difference matters. A false extreme can make a mystery feel bigger than it is. A corrected measurement can make the same mystery feel more real because it survives the correction. Uranus is not simply failing one test. It is pressuring several tests at once. Its rotation is extreme. Its magnetism is lopsided. Its heat flow is weak relative to expectation. Its atmosphere is less visibly active than Neptune's. Its moons and rings share the planet's sideways geometry. Any explanation has to connect those facts without pretending the data are stronger than they are. The first temptation is to call Uranus a broken planet. But that word is dangerous. Broken compared to what? Compared to Jupiter? Compared to Saturn? Those are gas giants dominated by hydrogen and helium. Uranus and Neptune are ice giants, a name that is slightly misleading because the ices inside them are not frozen like ice on Earth. In planetary science, ice refers to volatile compounds such as water, ammonia, and methane. Deep inside Uranus, these materials are hot, dense, compressed fluids, and perhaps in some regions exotic phases of matter that do not behave like familiar liquids or solids. This difference is central. Jupiter and Saturn are not scaled-up versions of Uranus. Uranus is not a failed Jupiter. It is a different category of world. Most of its mass is thought to be made of hot, dense, volatile-rich material above a smaller rocky core, with a hydrogen-helium envelope outside. Neptune is similar in broad composition. Both are smaller than the gas giants, but far more massive than Earth. They are the bridge between rocky worlds and hydrogen-dominated giants. And that bridge may be one of the most common places planets end up. Exoplanet surveys have revealed many worlds between Earth and Neptune in size. They are often called super-Earths or sub-Neptunes, depending on their radius, mass, and atmosphere. Our solar system has no close-in mini-Neptune, yet the galaxy seems full of them. That makes Uranus and Neptune more important than their distance suggests. They are not just outer planets. They are local laboratories for interpreting thousands of distant worlds. This is why the debate matters. If Uranus is merely a damaged oddity, then it tells us mainly about one ancient accident. But if Uranus is revealing normal ice giant physics under extreme circumstances, then it tells us about the largest missing chapter in planetary science. Voyager 2 is where the modern mystery became unavoidable. On January 24, 1986, the spacecraft made the first and still only close flyby of Uranus. It had already visited Jupiter and Saturn. It would later go on to Neptune. At Uranus, it had only a brief window for close observation because its trajectory was designed as a flyby, not an orbital mission. The encounter geometry was difficult. Because Uranus was tilted almost sideways, Voyager approached a system whose moons and rings appeared arranged like a bullseye from the spacecraft's perspective. The planet that filled Voyager's cameras did not look dramatic. In visible light, Uranus appeared almost featureless. It was not truly featureless, but compared with the busy belts of Jupiter or the storms of Neptune, it looked strangely blank. That appearance became part of Uranus's reputation. The planet looked boring, and yet the instruments were measuring the opposite of boring. The magnetometer found the tilted, offset magnetic field. The imaging system revealed moons and rings aligned with the planet's sideways equator. Atmospheric measurements suggested high winds, but little visible cloud contrast. Infrared and energy balance measurements fed the long-standing cold case problem of weak internal heat. Voyager did not solve Uranus. Voyager made Uranus scientifically urgent. The frustrating part is that Voyager could not stay. It could not map the magnetic field over many rotations from different angles. It could not measure seasonal changes across decades. It could not drop an atmospheric probe. It could not trace the gravity field with the precision an orbiter could achieve. It gave planetary scientists one brilliant slice through a complicated system, and then left forever. That is why every explanation remains partly provisional. We are building interior models of a planet we have never orbited, using a single close flyby, remote telescope observations, laboratory physics, numerical simulations, and comparison with Neptune. That is not nothing. It is enough to frame the right questions. But it is not enough to end the debate. Start with the tilt, because it is the most visible wound. A planet tilted by 98 degrees almost demands a story. The simplest story is impact. In the violent early solar system, Uranus may have been struck by a large protoplanet, perhaps one to several Earth masses, in a grazing collision that transferred angular momentum and knocked the young ice giant onto its side. This is not wild speculation in the general sense. Giant impacts were part of planet formation. The leading explanation for Earth's moon involves a giant impact with the early Earth. Mercury's large metallic core may preserve the aftereffects of mantle stripping or unusual formation processes. The early solar system was not a gentle place. A large collision with Uranus is physically plausible. A grazing impact is especially attractive because it can tilt a planet more efficiently than a head-on collision. A direct hit delivers energy, but not necessarily the right angular momentum. A glancing blow can spin and tip the target, like striking a ball off-center. Simulations show that such impacts can reproduce Uranus's extreme obliquity under certain conditions. They can also create a debris disk around the tilted planet, from which moons and rings could later form in the new equatorial plane. That matters because the moons are a constraint. If Uranus had formed upright with moons in an ordinary equatorial disk, and then was suddenly knocked over after the moons were already settled, those moons might not automatically follow. Some could be destabilized. Some could remain in an old plane. Some could be lost. Yet the regular moons and rings of Uranus are aligned with the planet's current equator. A post-impact debris disk that reforms the moon system offers a way to explain why the satellites share the tilt. But the impact hypothesis has a problem. A giant impact energetic enough to tip Uranus should also heat and mix the interior. If it thoroughly mixed the planet, heat should move out more easily. A well-mixed interior should convect. A convecting interior should release more internal heat and might generate a more deeply organized magnetic field. Uranus, by contrast, appears to have a stratified or otherwise inhibited interior, with muted heat flow and a dynamo that may operate in a shell rather than a deep central region. This is the first real counter-argument to the dramatic impact story. The same collision that explains the tilt may make the thermal and magnetic anomalies harder to explain. If you hit Uranus hard enough to knock it over, why did you not stir it into a planet that should glow and convect more like Neptune? Modern simulations have tried to rescue the impact model by making it more subtle. Perhaps the impact was grazing enough that it deposited most of its energy in the outer layers rather than mixing the whole planet. Perhaps material from the impactor became embedded at intermediate depths, creating a dense or high-entropy layer that inhibited convection below it. In that version, the impact does not merely tilt Uranus. It helps create the internal stratification that later traps heat and confines the dynamo. That modified impact scenario is powerful because it links several anomalies. The impact explains the tilt. The impact-generated disk explains the tilted moon system. The embedded material, or altered thermal profile, explains suppressed heat transport. The resulting shell-like conducting region explains the tilted magnetic field. One ancient event becomes the seed of the whole mystery, but it comes at a cost. The impact must be just right. Not too direct, not too mixing, not too weak, not too destructive. The composition of the impactor must matter in the right way. The timing must allow the moon system to form or reorganize. The outcome must preserve enough atmosphere and create the right internal layering. It is plausible, but it is not inevitable. A second explanation avoids a single catastrophic collision and looks instead to the slow violence of orbital migration. Early in solar system history, the giant planets likely did not sit exactly where they sit now. Jupiter, Saturn, Uranus, and Neptune interacted with a disk of small, icy bodies. Over time, they migrated. In some models, Uranus and Neptune may even have swapped relative positions during the outer solar system's rearrangement. During that chaotic era, gravitational resonances could have altered not just orbits, but spin axes. A planet's axis can precess, slowly tracing a cone in space. If that precession locks into a resonance with orbital motion, the tilt can be pumped upward over time. This is not fantasy. Spin-orbit resonances are real dynamical mechanisms. They can change planetary obliquities without requiring a single world-sized impact. For Uranus, a gradual resonance has one major advantage. If the tilt changed slowly, the moons could follow the changing equator. The satellite system would not need to be destroyed and rebuilt. It could be carried along as the planet's spin axis drifted toward its extreme position. This neatly addresses one of the hardest constraints on the impact model. But resonance has its own weakness. It explains the tilt better than it explains the rest. It does not naturally explain why Uranus has such a muted internal heat flow compared with Neptune. It does not naturally explain the shell-like magnetic geometry. It does not obviously explain why the atmosphere appears less energetically driven. To make resonance solve the whole problem, you have to add another mechanism for the interior. At that point, the story becomes a combination, not a single cause. A third line of explanation begins not with collisions or orbital migration, but with materials under pressure. What is Uranus made of deep inside? The honest answer is that we do not know in detail. We know its mass, radius, gravitational field at limited resolution, atmospheric composition at the top, and magnetic field from one flyby. The deep interior is model territory. That territory is stranger than the word ice suggests. At the pressures inside Uranus, water, ammonia, and methane do not behave like the substances we know on Earth. Water may enter superionic phases, where oxygen atoms form a lattice, while hydrogen ions move through it. Methane may break apart, and carbon may reorganize. Ammonia and water mixtures may conduct electricity in ways that are still being tested experimentally and simulated computationally. The interior of Uranus is not a cold snowball. It is a high-pressure chemistry laboratory the size of a planet. If some layers become stable against convection, they can trap heat. Convection is the efficient way for planets to move heat outward. Hot material rises, cool material sinks, and energy is carried by bulk motion. But if density increases in a way that resists overturning, or if a compositional gradient creates stable layering, then heat must leak by conduction. A much slower process. A planet can remain hot inside while appearing cold or only weakly warm outside. This is the thermos model of Uranus. Not a dead interior, but an insulated interior. Heat exists, but it is blocked. The surface energy balance looks muted not because the planet has no primordial heat, but because the path from deep interior to atmosphere is throttled. That same layered interior can explain the magnetic field. If only a relatively shallow shell of electrically conducting fluid is convecting, then the dynamo is not deep and spherical like Jupiter's. It is thin, off-center in effect, and geometrically complex. Such dynamos can produce tilted, multipolar fields. Neptune's magnetic field, also tilted and offset, supports the idea that ice giants may naturally generate fields differently from gas giants. In this view, Uranus does not break the dynamo rule. It reveals that there are different dynamo rules for ice giants. The strongest objection is again serious. If superionic or stratified layers explain Uranus, why does Neptune not behave the same way thermally? Neptune is only somewhat more massive than Uranus. It has a broadly similar composition. It also has a strange magnetic field. Yet Neptune emits much more internal heat and shows much more visible atmospheric activity. Any interior phase explanation has to account for the difference between the two planets, not just Uranus in isolation. One possibility is that Neptune's interior temperature profile differs enough to keep similar materials in more convective states. Another is that Uranus experienced an ancient impact or formation path that created stronger layering, while Neptune remained better mixed. Another is that both planets contain complex layering, but the details of heat transport differ because small changes in composition, temperature, or formation history produce large long-term effects. The uncomfortable truth is that we do not yet know. This is where the best claim becomes less dramatic but more scientifically honest. Uranus may be the product of multiple processes. A collision may have tilted it and altered its interior. Migration may have shaped its orbital and spin history. High-pressure phases may now regulate its heat flow and magnetic field. The planet is probably not a mystery with one key, but a locked system with several keys turned in sequence. That makes for a less clean story than the popular version. It is not as simple as a giant object smashed Uranus sideways and everything followed. It is also not as simple as Uranus was slowly tilted by resonance and nothing else happened. And it is not as simple as superionic ice solved the whole problem. The science is messier because the planet is messier. But this mess is not a weakness. It is the point. Real planets are historical objects. They are not just solutions to equations. They carry memory. Their spins, interiors, atmospheres, moons, rings, and fields are records of formation, collision, migration, cooling, chemistry, and time. Uranus is difficult because all those records overlap. The atmosphere is the most deceptive record because it looks so quiet. Voyager's images made Uranus seem almost inactive, yet later observations have shown that it does have clouds, storms, hazes, winds, and seasonal change. The question is not whether Uranus has weather. It does. The question is why its weather looks so subdued compared with the forcing it experiences and compared with Neptune. The tilt should create extreme seasons. For decades, one hemisphere receives sunlight while the other remains in darkness. If solar heating alone drove the weather, the atmospheric response should be dramatic. Yet the visible contrast remains muted One likely reason is that internal heat, not sunlight alone, helps drive giant planet weather. Neptune, far from the Sun, is active because it has a strong internal heat flux. Uranus receives more sunlight than Neptune, but has weaker internal heat, so its weather engine may be starved from below. There is also the haze. Uranus's atmosphere contains methane, which absorbs red light and helps create the blue-green color. Sunlight breaks methane apart in the upper atmosphere, creating photochemical products that form hazes. Uranus appears paler and more muted than Neptune, partly because its haze structure differs. A thick haze can hide deeper clouds from visible light cameras, making an active atmosphere look smoother than it really is. Infrared observations, which peer through some of the haze, reveal more structure. So the atmosphere is not dead, it is veiled. And the veil itself may be a consequence of the planet's weak heat flow and seasonal geometry. A muted interior changes the atmospheric temperature structure. That changes cloud formation and haze chemistry. That changes what telescopes can see. The visible calm becomes another symptom of deep interior physics. This is why Uranus is so frustrating. It refuses to let us separate surface from depth. The tilt affects seasons. The seasons affect sunlight and chemistry. Heat flow affects atmospheric vigor. Interior layering affects heat flow and magnetic field geometry. The magnetic field affects the magnetosphere and auroras. The moons and rings constrain the timing of the tilt. Pull one thread, and the whole planet moves. The magnetic field may be the most direct clue to the interior because magnetic geometry is not cosmetic. It is a map of conducting motion. A tilted, offset field tells us that the dynamo is unusual, but recent work also reminds us to be careful. A single flyby may have sampled the magnetosphere under unusual solar wind conditions. External forcing can change what a spacecraft measures. The intrinsic field is real, but the flyby context matters. Again, the pattern repeats. The old dramatic claim is softened, but the mystery remains. Uranus's moons add another layer. The classical moons, Miranda, Ariel, Umbriel, Titania, and Oberon, orbit in the planet's tilted equatorial plane. Voyager images showed complex surfaces, especially Miranda, whose broken terrain looks like a world assembled from mismatched geological provinces. Some Uranian moons may have experienced internal heating, and could even have subsurface ocean histories, though this remains uncertain. A Uranus mission would not merely study the planet. It would study a full system: planet, rings, moons, magnetosphere, and the long aftermath of whatever tilted the whole architecture. The moons are especially important because they may preserve records the planet's atmosphere does not. An atmosphere changes. A magnetic field changes. But icy moon surfaces can preserve tectonic fractures, resurfacing events, crater histories, and signs of past internal heat. If Uranus was struck by a giant impact, the moon system may carry clues. If the moons formed from a debris disk after the tilt, their compositions and orbital histories should reflect that. If they predate the tilt and were carried along by resonance, the evidence might differ. A dedicated orbiter could distinguish these possibilities by measuring gravity, magnetic fields, moon geology, ring dynamics, and atmospheric composition over time. It could watch Uranus rotate. It could map the magnetic field globally instead of along one path. It could drop a probe into the atmosphere and measure noble gases, methane, water, ammonia, hydrogen sulfide, and isotopic ratios directly. These measurements would constrain where Uranus formed, how it migrated, and how much heavy material it contains. That is why the Uranus orbiter and probe became the highest priority new flagship mission recommended by the Planetary Science Decadal Survey for the 2023 to 2032 decade. The scientific logic is not simply that Uranus is weird. It is that Uranus sits at the intersection of several major unsolved problems: how ice giants form, how they migrate, how their interiors work, how their magnetic fields are generated, whether their moons are ocean worlds, and how to interpret the most common exoplanet sizes. The exoplanet connection may be the deepest consequence. Kepler and other surveys showed that planets between Earth and Neptune in size are common. They may have thick hydrogen envelopes, water-rich interiors, rocky cores, high-pressure fluids, or combinations that do not appear in our own inner solar system. When astronomers observe such a planet, they often have only mass, radius, orbital period, stellar properties, and perhaps a spectrum. From that, they infer composition. But those inferences depend on interior models. If our Uranus model is wrong, then our sub-Neptune models may be wrong too. A planet's mass and radius do not uniquely reveal whether it is rock-rich, water-rich, gas-rich, layered, mixed, hot inside, magnetically protected, or vulnerable to atmospheric loss. Different interiors can produce similar bulk densities. Different heat histories can produce similar radii. Different atmospheric compositions can mask deeper structures. Uranus is a reminder that the same outside can hide very different insides. Consider a distant sub-Neptune orbiting a red dwarf. If it has a strong, stable magnetic field, it may retain its atmosphere despite stellar flares. If its magnetic field is tilted, offset, weak, or highly variable like an ice giant shell dynamo, atmospheric escape calculations change. If its interior is stably layered, it may cool slowly and maintain hidden internal heat. If it is well mixed, its thermal evolution may be different. These are not details. They shape whether a world remains geologically active, whether it outgasses, whether it keeps an atmosphere, and whether some form of habitability is plausible. This does not mean Uranus tells us which exoplanets are habitable. That would be too strong. Uranus is not habitable in any Earth-like sense, and most sub-Neptunes are likely hostile to life as we know it. But Uranus tells us how dangerous overconfidence can be. If one accessible ice giant can surprise us this much, distant worlds with only 2 measured numbers should humble us even more. The old model of planetary classification was simple: rocky planets inside, gas giants outside, a few icy bodies beyond. Exoplanets shattered that simplicity. Hot Jupiters orbit close to their stars. Super-Earths exist in abundance. Mini-Neptunes are common. Planets migrate. Atmospheres escape. Some worlds may be water-rich. Some may be stripped cores. Some may be inflated by heat. Some may be hidden beneath haze. The galaxy did not build planets only in the categories our solar system happened to show us first. Uranus therefore belongs to a larger scientific correction. It tells us that the solar system is not a universal template. It is one outcome. A precious outcome because it is close enough to study, but still only one. Uranus and Neptune are the only local examples of ice giants, and one of them is deeply anomalous, while the other is less understood than it should be. Our sample size is 2. Our confidence should match that. The evidence points toward a clearer distinction. The wrong lesson is that Uranus is a joke planet that breaks all the rules. The better lesson is that Uranus reveals where our rules were built from too small a sample. We mistook gas giant behavior for giant planet behavior. We mistook visible calm for physical simplicity. We mistook weak heat flux for no heat. We mistook one flyby for enough. A planet can look boring and still be revolutionary. The strongest opposing view says that we may be over-interpreting. Uranus's heat budget has recently been revised upward. Its atmosphere is more dynamic than Voyager's visible images suggested. Neptune's magnetic field is also tilted and offset, so Uranus may be less unique magnetically than once thought. Some anomalies might weaken with better measurements. A cautious scientist could argue that Uranus is not rewriting planetary science. It is simply underobserved. That argument is partly right. And because it is right, it has to be included. Uranus has suffered from neglect. Some of its reputation comes from insufficient data. More observations have already softened older claims. The planet is not frozen into the exact picture Voyager delivered in 1986. It changes. It has seasons. It radiates some internal heat. It has clouds. It is not the dead blank sphere of old textbook images. But underobserved is not the same as unimportant. In fact, underobserved makes it more important. The revised heat measurement does not make Uranus ordinary. It refines the anomaly. The atmospheric activity does not make the tilt irrelevant. It shows that the response is complex. Neptune's similar magnetic weirdness does not erase the magnetic problem. It expands it from Uranus to ice giants as a class. The counter-argument does not defeat the claim. It redirects it. The mystery is not that Uranus violates every rule in isolation. The mystery is that the entire ice giant category may require rules we have not finished discovering. Think of how science often advances. Not when a phenomenon is completely inexplicable, but when it is almost explicable, and one stubborn detail remains. Mercury's orbit was almost explained by Newtonian gravity, except for a small perihelion shift. That small difference became a doorway into general relativity. The ultraviolet catastrophe was a problem in radiation theory, not a mystical event, and it became one doorway into quantum mechanics. The point is not that Uranus is about to produce an equivalent revolution. The point is that stubborn mismatches matter because they reveal the limits of a model. Uranus's mismatches are not small in geometry. A 98-degree tilt is not a rounding error. A magnetic field tilted by nearly 60 degrees and offset by a third of a radius is not a minor correction. A heat flux far weaker than Neptune's is not trivial. These are large clues attached to a planet we can actually reach. The reaching matters. We cannot send orbiters to sub-Neptunes around distant stars. We cannot drop probes into their atmospheres. We cannot map their magnetic fields directly with spacecraft. But we can do those things at Uranus. That makes it a local proxy for a galactic problem. A Uranus orbiter and probe would answer several questions no telescope can. What is the true bulk composition of Uranus? How much water is there? How much ammonia? How much methane? What are the noble gas abundances which preserve formation clues because noble gases do not easily participate in chemistry? How deep do winds penetrate? Where is the dynamo generated? How multipolar is the field? Is the interior sharply layered, gradually stratified, or something stranger? How much heat is truly escaping over a full seasonal cycle? Which moons may have had or still have subsurface oceans? Each answer would ripple outward into exoplanet science. If Uranus is strongly layered, sub-Neptune interiors may need more layered models. If its magnetic field comes from a shallow conducting shell, magnetic protection around similar exoplanets may be more variable than simple dipoles suggest. If its heat budget is controlled by subtle atmospheric reflectivity and seasonal variation, exoplanet thermal measurements may be harder to interpret than we think. If its moons show ocean world signatures, then ice giant satellite systems become more interesting astrobiological environments than their distance from the Sun would suggest. There is also a philosophical correction here, though it must be grounded in science. We often imagine the solar system as familiar because we have named its planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The names make them feel domesticated. But naming is not understanding. Uranus has had a name since the 18th century. It has had telescopic observations for centuries. It has had one spacecraft visit. And still, the planet can look back at our models and quietly say, not enough. One reason Uranus stayed neglected is aesthetic. Jupiter is dramatic. Saturn is beautiful. Mars is emotionally close. Venus is terrifying. Europa and Enceladus tempt us with oceans. Uranus seemed pale, distant, and uncharismatic. Even its name became a distraction. But science is often least sentimental where it is most important. The boring planet may be the one that breaks a hidden assumption. The word break needs care. Uranus does not break physics. It obeys gravity, thermodynamics, magnetohydrodynamics, radiative transfer, and high-pressure chemistry. The planet is not impossible. It is lawful. What it breaks is our simplified expectation of what a planet like it should do. That distinction is the difference between responsible wonder and empty hype. Responsible wonder says, here is a lawful object whose laws we have not fully mapped. Empty hype says, everything we know is wrong. Everything we know is not wrong. Planet formation theory explains much. Dynamo theory explains much. High-pressure physics explains much. Voyager's data were not a failure of the old science, but a challenge to extend it. The point is not to tear down the model. It is to make the model honest enough to include Uranus. The best current picture may be something like this. Uranus formed in the outer solar system, perhaps not exactly where it sits now. During the era of giant planet migration, its orbit and spin history were shaped by gravitational interactions. At some early stage, a major impact or sequence of impacts may have altered its obliquity and deposited material in a way that helped create stable interior layering. Deep inside, volatile-rich materials under extreme pressure may form conducting and insulating regions unlike anything in gas giants. Heat transport became inefficient. A shallow conducting shell powered a lopsided magnetic field. Weak heat flow muted the atmosphere, while haze and seasonal geometry shaped what we see. The moons and rings, either formed from post-impact debris, followed a slow tilt, or preserve a more complicated history that only an orbiter can untangle. That picture is not final. It is a scaffold. Some beams may be removed, some may be strengthened, some may collapse under better data, but it has the virtue of treating Uranus as an integrated system, not a list of curiosities. The integrated system view is essential because planets are not independent facts stacked on top of each other. A magnetic field is an interior clue. An atmosphere is a heat flow clue. A moon system is a formation history clue. A ring system is a dynamical clue. A tilt is a fossil of angular momentum. A heat budget is a fossil of cooling and layering. Uranus is not just telling us that it is sideways. It is telling us that sidewaysness, heat, magnetism, atmosphere, and satellites may be linked through one long history. There is also time. Uranus has been orbiting the Sun for billions of years. Its seasons are long by human standards, but brief by planetary standards. Since Voyager, Uranus has moved from solstice toward equinox and beyond, letting telescopes see changing illumination. The planet's northern hemisphere has emerged into sunlight. Cloud activity has changed. Bright polar caps and storms have appeared. A single flyby at one season cannot represent a planet whose year lasts 84 Earth years. Observing Uranus properly requires patience measured not in hours, but in decades. That is another lesson for exoplanets. Many distant worlds are observed in snapshots. We catch a transit, a spectrum, perhaps repeat observations across a few orbits. We infer climate, atmosphere, composition, and sometimes habitability from limited windows. Uranus reminds us that planets can have deep seasonal cycles, hidden layers, delayed atmospheric responses, and histories that cannot be read from one moment. If you want the strongest version of the skeptic's argument, it is this. Uranus may be scientifically fascinating, but it is not necessarily a universal key. Sub-Neptunes around other stars often orbit much closer to their stars than Uranus does. They may have different irradiation, different atmospheres, different masses, different formation histories. Many may not be true Uranus analogs. They may be rocky cores with hydrogen envelopes, water worlds, evaporating mini-Neptunes, or something else. Using Uranus as a Rosetta Stone could mislead us if we treat it too broadly. That is fair. Uranus is not every sub-Neptune. A cold outer ice giant in our solar system is not the same as a close-in planet blasted by a red dwarf or a hot mini-Neptune stripped by stellar radiation. The analogy must be used carefully. But without Uranus, we have even less. A local, reachable ice giant gives us ground truth for high-pressure, volatile-rich planetary interiors. It gives us one anchor point. Neptune gives another. The goal is not to make Uranus a universal template, but to stop interpreting the galaxy with no nearby calibration at all. Ground truth matters because remote sensing is ambiguous. A spectrum can show water vapor in an atmosphere, but not easily tell you whether the planet has a deep ocean, a steam layer, a high-pressure ice mantle, or a hydrogen envelope above water-rich fluid. A mass and radius can suggest low density, but not uniquely reveal internal layering. A transit can show size, but not magnetic protection. To interpret remote worlds, we need local worlds where the hidden interior can be constrained by gravity, magnetism, heat, and composition together. Uranus is one of the only places to do that. The mission question is therefore not merely why go to Uranus. It is why we waited so long. A spacecraft sent there would take many years to arrive. It would require careful trajectory planning, likely gravity assists, nuclear power, and a payload built for faint sunlight and extreme cold. It would not be a quick mission. Outer solar system exploration never is. But the scientific return would be enormous because the uncertainty is enormous. The less you know about a system, the more every precise measurement matters. Cassini transformed Saturn because it stayed. It watched rings change, storms evolve, moons orbit, plumes erupt from Enceladus, methane cycles unfold on Titan. Juno transformed Jupiter's deep interior picture because it measured gravity and magnetic fields from orbit. Galileo changed Jupiter's atmosphere with a probe. Voyager revealed Uranus, but only as a question. An orbiter would turn the question into a map. The atmospheric probe may be especially important. Remote observations can estimate some atmospheric species, but they struggle with deep abundances, especially water. A probe descending through Uranus's atmosphere could directly measure composition with altitude. Noble gases would reveal formation conditions. Isotopic ratios would constrain origin and evolution. Temperature and pressure profiles would test atmospheric models. Wind measurements during descent would reveal circulation at depths unseen from orbit. The gravity field would test the interior. Tiny changes in the spacecraft's motion would reveal how mass is distributed inside Uranus. Different models predict different gravitational harmonics. A sharp compositional boundary, a gradual gradient, a rock-rich interior, a volatile-rich mantle, a superionic layer, a post-impact stratification. These are not equally invisible to a good gravity experiment. The planet's pull would tell us which interiors are plausible. The magnetic field would test the dynamo. An orbiter could map the field over many rotations and many positions, separating intrinsic field structure from changing solar-wind interactions. It could determine how strong the multipole components are, where the dynamo is likely operating, and how the magnetosphere opens and closes as the tilted field rotates. It could connect auroras, particle environments, rings, moons, and atmospheric loss. The moons would test history. Miranda's fractured terrain, Ariel's resurfacing, Titania and Oberon's ancient surfaces, possible ocean signatures, crater distributions, orbital dynamics, ring interactions. Each is a page in the Uranian system's archive. If a giant impact created the satellite system, the moons may preserve compositional and dynamical clues. If some moons have or had oceans, Uranus becomes not only an ice giant problem, but an ocean world system, and the rings, dark and narrow, may preserve collisional history. They are not Saturn's bright display. They are quiet, thin structures whose particles may carry information about moon disruption, dust production, and dynamical confinement. In a system where the whole equatorial plane lies sideways, even the rings become part of the tilt story. The phrase "the planet that broke every rule therefore needs correction." It is good drama, but incomplete science. Uranus did not break the rules of nature. It broke our borrowed rulebook. It showed that a rule based on gas giants might fail for ice giants. It showed that a single close flyby is not enough. It showed that planet formation is not just orderly disk accretion, but also impact, migration, resonance, phase transition, stratification, and long-term cooling. The rewritten claim is stronger because it is more precise. Uranus is not a cosmic mistake. It is a physical archive of how ice giants become different from the planets we understood first. The archive is hard to read because its pages are layered. The tilt is written in angular momentum. The heat is written in thermodynamics. The magnetic field is written in conducting fluids. The atmosphere is written in methane, haze, seasons, and hidden energy. The moons are written in ice, craters, fractures, and orbital planes. The exoplanet connection is written in the statistics of worlds we can barely see. When people laugh at the name, the planet remains what it is. A 14.5 Earth mass laboratory of high-pressure planetary physics, orbiting 19 astronomical units from the Sun, carrying clues about why one ice giant is thermally muted while another glows, why both ice giants have strange magnetic fields, why some planets lie sideways, and how the most common planetary sizes in the galaxy may actually work. There is a humbling irony in that. The planet that looks least expressive may be telling us one of the most important stories. It tells us that the universe does not owe us categories that are easy to teach. Gas giant, ice giant, rocky planet, super-Earth, mini-Neptune. These labels are useful, but they are not reality itself. They are maps. And Uranus is the kind of territory that tears holes in maps. A good map can be repaired. That is what science does. It does not protect old categories because they are comfortable. It follows the anomaly until the category changes. To make the argument fully honest, we have to slow down around the word rule. A rule in planetary science is not the same thing as a law, like conservation of energy. A law is a constraint nature must obey. A rule is often a pattern we infer from the cases we have seen. When the sample is small, the rule can look stronger than it really is. For centuries, the solar system was the only planetary system we knew. Even after exoplanets were discovered, detailed planetary physics still leaned heavily on the worlds close enough to measure directly. That means our first generalizations were shaped by a particular family: 4 small rocky planets, 2 gas giants, and 2 ice giants at the edge. The gas giants were easier to admire and, in some ways, easier to model. Jupiter is massive, bright, stormy, magnetic, and internally warm. Saturn is ringed, luminous, structured, and rich in observational clues. Uranus and Neptune were distant, dim, and visited only once each. So the mental picture of giant planets became biased toward Jupiter and Saturn. That bias is understandable. It is also dangerous. If you learn from gas giants first, you expect deep hydrogen-rich interiors, powerful heat flow, and dynamos organized by large conducting regions. Then you look at Uranus and wonder why the field is crooked, why the heat is muted, why the atmosphere looks veiled, and why the planet lies sideways. But perhaps the more honest question is not why Uranus failed to become Jupiter. It is why we expected it to behave like Jupiter in the first place. Uranus is dominated by materials whose behavior at depth remains experimentally difficult. We can compress samples between diamonds and shock them with lasers, but a planetary interior is not a laboratory cell. It is huge, layered, rotating, slowly cooling, and chemically mixed across billions of years. It may contain gradients rather than boundaries, partial mixing rather than clean shells, and phases that change with pressure, temperature, and composition in ways still being mapped. The models are improving, but the planet is still ahead of the model. Even the phrase ice giant carries hidden assumptions. The ice inside Uranus is not a block of frozen water. It is a family of volatile, rich materials under pressures millions of times greater than Earth's surface atmosphere and temperatures high enough to destroy familiar chemistry. Water can become ionic or superionic. Methane can dissociate. Ammonia can participate in conductive mixtures. Carbon may separate in ways that have inspired ideas about diamond formation, though such claims need caution because the interior conditions and quantities remain debated. The deeper message is simpler. The inside of Uranus is not made from everyday substances behaving in everyday ways. This is where the interior and the magnetic field meet. A deep, convecting, electrically conducting sphere tends to make a strong dipole. A thin, convecting shell can make a field with large non-dipole components. If the conducting shell is not centered in the same way as the planet's mass distribution, the external field can look tilted and offset. Uranus's field is not random. It is a clue to where electrical currents are flowing. The fact that Neptune also has an offset and tilted field is therefore not a dismissal of Uranus's strangeness. It is evidence that ice giants may generate magnetic fields in a way that is fundamentally different from gas giants and terrestrial planets. The thermal story has the same structure. If heat is carried efficiently upward, a young giant planet can remain luminous for billions of years. If heat is trapped by stable layering, the planet can hide internal energy for long periods. Recent studies suggesting Uranus emits more heat than once believed are important because they prevent the story from becoming false drama. The planet is not a corpse. But it is still underluminous relative to the older comparison with Neptune. What matters is not the absolute claim of zero internal heat. What matters is the contrast, the muted leakage, and the possibility that Uranus's deep interior is separated from its visible atmosphere by layers that slow the entire cooling process. That possibility changes the impact debate. A giant impact does not simply knock a planet over like a toy, it changes the distribution of entropy, composition, angular momentum, and debris. It can remove atmosphere, bury impactor material, create orbiting disks, and modify stratification. Depending on angle and speed, a collision can mix a planet or leave much of the deep interior intact. The question is not whether an impact happened. The question is, what kind of impact, at what time, into what pre-existing interior, and with what long-term thermal consequences. A gradual resonance does not remove the need for an interior story either. It may help explain why the moons share the tilt, but it does not automatically produce suppressed heat. It may be part of the sequence, rather than the whole sequence. The same is true of high-pressure phase barriers. They may explain heat and magnetism, but not the obliquity. Uranus forces a multi-cause explanation because its observations live in multiple physical domains. This is why a simple scoreboard can be misleading. One hypothesis may win on tilt and lose on heat. Another may win on heat and lose on moons. Another may explain the dynamo, but not the formation history. The real answer may not be the hypothesis that wins every category alone, but the combination that leaves the fewest contradictions when the planet is treated as one evolving body. That is less tidy than a one-cause explanation, but it is closer to the evidence. For science, it is more powerful. Nature does not owe us one-cause narratives. A planet may be the product of a disk, a migration, an impact, a phase transition, a heat barrier, and a billion-year seasonal cycle. The art is not to simplify those into a myth, but to make the complexity feel coherent. Uranus deserves that coherence because its mystery is not isolated from the rest of planetary science. The next generation of telescopes will deliver better spectra of sub-Neptune atmospheres. They will detect water, methane, carbon dioxide, haze, clouds, perhaps disequilibrium chemistry in some cases. But spectra tell us mostly about upper atmospheres. To know what those atmospheres mean, we need interiors. We need formation pathways. We need thermal histories. We need magnetic context. The distant planet and the local ice giant are part of the same scientific problem. A sub-Neptune with a radius 3 times Earth's and a mass 8 times Earth's, can be interpreted in several ways. It might have a rocky core and a thin hydrogen envelope. It might be water-rich. It might have a deep atmosphere with no surface. It might have layers where pressure turns familiar molecules into exotic phases. Without ground truth, models can fit the same mass and radius with different interiors. Uranus cannot solve that ambiguity alone, but it can narrow the physics that models are allowed to use. That is why the next Uranus mission, if it flies, will not be merely a return visit. It will be a calibration mission for the galaxy. It will turn one of the weakest points in our planetary knowledge into one of the strongest. It will take the pale blue-green disk that Voyager saw for hours and make it a world observed over seasons, rotations, magnetic cycles, and moon encounters. It will replace a snapshot with a history. Until then, Uranus remains an argument, a planet arguing against overconfidence, a planet arguing against borrowed categories, a planet arguing that the most common worlds may not be the ones we understand best. And in that sense, its silence is not emptiness. It is a challenge. One way to see the scale of the problem is to compare Uranus with the planet it should resemble most. Neptune is not an identical twin, but it is the closest sibling Uranus has. The two worlds occupy the same broad class. They are similar in mass, similar in radius, similar in bulk density, and both are made largely of volatile-rich material beneath hydrogen-helium atmospheres. If planetary science had to pick a control experiment, Neptune would be it. And yet the comparison is almost cruel. Neptune is farther from the Sun, receiving less solar energy, but it looks more alive. Its atmosphere is deeper blue, more textured, more visibly restless. It has hosted dark spots, high-altitude methane clouds, and some of the fastest winds measured in the solar system. It emits more than twice the energy it receives from the Sun. Its magnetic field is also strange, which helps us avoid treating Uranus as the only ice giant anomaly. But Neptune's heat output makes it clear that an ice giant does not have to be thermally muted. Uranus is not simply doing what all ice giants do. This comparison creates a useful tension. On one side, Uranus and Neptune are similar enough that shared explanations are attractive. Their offset magnetic fields may tell us that ice giant dynamos naturally differ from gas giant dynamos. On the other side, they are different enough that shared explanations are incomplete. Neptune's strong internal heat and Uranus's muted heat demand a history or structure that diverged after the two planets formed, or perhaps even during formation itself. That means the question is not only what happened to Uranus, it is why Neptune escaped the same fate, or why Uranus escaped whatever made Neptune more luminous. The answer may involve where they formed, how fast they formed, how much solid material each accreted, how much gas remained in the disk, whether they migrated through different regions, whether one or both suffered giant impacts, and how high-pressure materials behave under slightly different thermal profiles. Even the origin locations of Uranus and Neptune remain uncertain. In some migration models, Neptune formed closer to the Sun than Uranus and later moved outward, while Uranus ended up inside Neptune's present orbit. That possibility sounds dramatic, but the outer solar system almost certainly underwent a major rearrangement. The modern spacing of the giant planets is not simply a fossilized copy of their birth positions. The small body populations of the Kuiper Belt, the resonant orbit of Pluto, and the architecture of distant icy objects all point to migration. If Uranus and Neptune migrated, then their interiors may preserve different formation environments. A planet forming closer in may incorporate different solids, different gases, and different ratios of water, ammonia, methane, rock, and hydrogen. A planet forming later may accrete less nebular gas. A planet scattered through a disk of planetesimals may suffer different impacts. Two planets that look like siblings today may have followed very different childhoods. That is one reason an atmospheric probe is so valuable. Noble gases can act like planetary receipts. Because they are chemically reluctant, their abundances preserve information about the conditions under which a planet captured its atmosphere. Argon, krypton, xenon, and isotopic ratios do not tell a simple story by themselves, but they can distinguish between formation scenarios. They can reveal whether Uranus's envelope resembles a solar composition enriched in certain ways, or whether it carries fingerprints of cold-trapped materials from farther out in the disk. Water abundance matters just as much. Water is not merely one ingredient among many. It is a major oxygen carrier and a key indicator of how much icy material the planet accreted. But measuring deep water abundance from Earth is extremely difficult because the water may be hidden below cloud decks and below the levels remote spectra can probe. A descent probe would not reach the deep interior, but it could measure the atmospheric profile directly enough to anchor models that now drift across wide uncertainty ranges. This is where the drama becomes very practical. We are not missing a poetic detail, we are missing numbers. We need gravity harmonics, magnetic multipoles, heat budgets, noble gas ratios, water enrichment, wind depth, cloud structure, ring masses, moon compositions, and seasonal behavior. These are not decorations. They are the variables that decide which physical model survives. Consider the heat problem again with the updated correction. If Uranus emits around 15% more energy than it receives from sunlight, then its interior is not sealed perfectly. Heat is escaping. The old phrase, almost no internal heat, is too blunt. But the comparison with Neptune still asks for explanation. Why does one ice giant leak modestly while the other radiates strongly? The difference may be a boundary. It may be a composition gradient. It may be an impact-created layer. It may be a difference in cloud reflectivity and seasonal averaging that earlier estimates mishandled. It may be more than one of these. A careful interpretation must therefore avoid two traps. The first trap is exaggeration. Uranus has zero internal heat, end of story. The second trap is overcorrection. Because Uranus has some heat, the problem is solved. Neither is science. The better statement is that Uranus's energy budget has become more nuanced, and that nuance strengthens the need for better measurements. The same is true of the atmosphere. Voyager's images made Uranus look blank, but Uranus is not truly blank. Hubble, Keck, and other telescopes have observed changing cloud features, seasonal brightening, storms, and polar haze. The atmosphere responds to the 84-year solar cycle, but not always in the simple way a first model might predict. That delayed or muted response is itself a clue to atmospheric depth, radiative timescales, methane condensation, and the balance between solar forcing and internal heat. A giant planet atmosphere is not like Earth's atmosphere with a solid ground underneath. There is no surface where weather stops. Pressure increases continuously as one descends. Clouds form at different depths depending on temperature and composition. Methane clouds, hydrogen sulfide clouds, ammonia-related chemistry, and haze layers may each occupy different regions. Winds may be shallow weather layer phenomena, or they may extend deep into the interior. Without an orbiter and probe, we cannot tell how much of what we see is surface weather and how much is the visible top of deep circulation. This matters because the atmosphere can hide the planet's engine. A smooth, visible disk may be an optical effect. If haze blankets the upper atmosphere, deeper storms can be hidden. If most cloud contrast appears in infrared, the planet looks calmer in visible light than it really is. If seasonal radiative time constants are long, the atmosphere may respond years or decades after maximum sunlight. Uranus is not necessarily lazy. It may be slow, veiled, and delayed. That is a different kind of mystery. A dead planet would be simple. A planet that responds weakly, late, and selectively is more interesting because it suggests hidden reservoirs and time lags. It suggests that the atmosphere is coupled to the interior in a way we have not measured. It suggests that one season of observation is not enough. The magnetic field also asks for time. A planet's magnetosphere is not just a static shape. It is an interaction between the internal field, the solar wind, plasma sources, moons, rotation, and the planet's orbital position. Uranus's rotation carries its tilted magnetic field through space every 17 hours. The solar wind compresses one side and stretches the other into a magnetotail. Because the dipole is offset, different regions of the atmosphere and magnetosphere experience very different magnetic environments over a single rotation. Auroras on Uranus therefore cannot be understood using a simple Earth analogy. On Earth, auroras cluster near magnetic polar regions that have a relatively stable relationship to the rotation axis. On Uranus, the magnetic poles are far from the geographic poles, and the whole configuration is tilted relative to the Sun in a way that changes with both rotation and season. The auroras are not just lights. They are diagnostics of the magnetic field, the solar wind, and the upper atmosphere. A future mission could treat the magnetosphere as a moving laboratory. It could watch how the field reconnects with the solar wind, how particles are accelerated, how moons sweep through plasma, how rings interact with charged grains, and how atmospheric escape may occur. That is not only a Uranus problem. Magnetospheres shape atmospheric retention and radiation environments throughout planetary systems. If ice giant magnetic fields are commonly offset and multipolar, then many exoplanets may have protective environments very different from the neat dipoles often assumed in simplified habitability discussions. The habitability angle must be handled carefully. Uranus itself is not a habitable planet in the familiar sense. Its atmosphere is crushing, cold at the visible levels, and deepening into hostile fluids. But the physics of magnetic shielding, atmospheric escape, and internal heat matters for worlds orbiting other stars, including sub-Neptunes and potentially their moons. A planet does not need to be habitable to teach habitability physics. This is similar to Jupiter. Jupiter is not habitable, yet understanding Jupiter helps us understand how giant planets shape comet flux, moon habitability, magnetospheres, and planetary system architecture. Uranus plays a parallel role for ice giants and sub-Neptunes. It is not a destination for life. It is a calibration for environments where life-related questions may be asked elsewhere. The moons of Uranus deserve more than a passing mention because they may turn out to be the most surprising part of the system. Miranda, with its patchwork terrain, suggests intense geological disruption or resurfacing. Ariel appears to have features that may reflect past internal activity. Titania and Oberon are large enough that internal oceans are not impossible under some thermal histories, though evidence remains indirect. If any Uranian moon has preserved or once hosted a subsurface ocean, then the system's scientific importance expands dramatically. Ocean worlds are not restricted to the warm inner solar system. Europa, Enceladus, Titan, Ganymede, Callisto, Triton, and perhaps other icy bodies teach us that liquid water can survive beneath ice when tidal heating, radiogenic heat, antifreeze compounds, or residual formation energy cooperate. Uranian moons receive less tidal heating than Europa or Enceladus in the modern system, but past orbital resonances or early heating could have mattered. The moons are not guaranteed ocean worlds, but they are plausible enough to deserve close measurement. If a Uranus orbiter found signs of ocean layers inside one or more moons, it would alter how we think about habitable niches around ice giants. If it found no such signs, that would also matter because it would define the limits of ocean world persistence in colder, less tidally active systems. Either result is valuable. The point is not to force an astrobiological promise onto every icy moon. The point is to let measurements decide. The rings are similarly understated. Uranus's rings are dark, narrow, and dynamically complex. They may be young, old, collisionally renewed, or connected to small moons that shepherd and confine them. Their darkness suggests processed material, perhaps altered by radiation and micrometeorite bombardment. Their structure records gravitational interactions and the history of small bodies near the planet. In a system where a giant impact may have created debris, rings become part of the forensic record. This is why a Uranus mission should not be imagined as a single planet mission. It is a system mission. The planet's interior, atmosphere, magnetosphere, rings, and moons are coupled. A magnetic field affects charged particles. Charged particles darken moon and ring surfaces. Moons shape rings. Rings and small moons preserve debris history. The planet's tilt changes seasonal illumination for every object in the system. The system is one machine with many visible parts. The broader consequence is that planetary science increasingly moves from object lists to system histories. A planet is not merely a mass, radius, and orbit. It is an outcome of time. It formed somewhere, accreted certain materials, migrated or did not, collided or did not, differentiated, cooled, stratified, lost gases, gained moons, altered moons, and interacted with stellar radiation. Uranus is valuable because its current oddities are historical evidence. The difficult part is that different histories can converge on similar present-day features. A giant impact and a gradual resonance can both affect tilt. A primordial composition gradient and an impact-generated layer can both suppress convection. A shell dynamo and a disturbed magnetosphere can both look complex to a flyby. This is why one measurement is rarely enough. The goal is to combine many independent lines of evidence until only a few histories remain possible. This is exactly what happened in other parts of planetary science. Mars was once interpreted through telescopic sketches and speculation. Orbiters, landers, rovers, and meteorites turned it into a layered history of water, volcanism, atmosphere loss, and climate change. Saturn's system changed from a ringed planet with interesting moons into a complex laboratory of ocean worlds, methane meteorology, ring dynamics, and magnetospheric chemistry, because Cassini stayed. Pluto changed from a point of light into a geologically active dwarf planet because New Horizons passed close. Uranus is still waiting for that transformation. The waiting has consequences. Every year without close ice giant data, exoplanet interpretation advances on uncertain foundations. Telescopes improve, catalogs grow, new atmospheres are detected. But the interior models still ask for anchor points. A Uranus mission would not answer every exoplanet question, but it would reduce the freedom of models to invent interiors that fit sparse data. It would make distant interpretations less arbitrary. There is a subtle danger in saying the galaxy is full of Uranuses. It is not literally true if we mean exact copies at the same temperature, distance, and history. Many sub-Neptunes are closer to their stars, warmer, perhaps more irradiated, perhaps stripped or inflated. Some may be fundamentally different from Uranus, despite similar radii. But if we mean that volatile-rich, Neptune to sub-Neptune scale planets are common and poorly understood, then Uranus is central. It is the reachable member of a vast family of worlds. The most honest metaphor is not that Uranus is the answer. It is that Uranus is the dictionary we have not opened. We are trying to translate exoplanet signals without fully understanding the language of ice-rich interiors. Uranus will not translate every word, but it can teach us grammar, how materials layer, how heat escapes, how magnetic fields form, how atmospheres hide their depths, and how violent histories leave durable signatures. The final caution is about humility. It is tempting to look at Uranus and decide in advance which explanation feels best. The giant impact is cinematic, the resonance is elegant, the superionic interior is exotic. The mission case is inspiring. But science is not a contest of beautiful stories. It is a contest of predictions. The winning explanation will be the one that survives gravity data, magnetic data, atmospheric chemistry, heat flow measurements, moon geology, and ring dynamics together. Until those data arrive, the correct stance is disciplined uncertainty, not ignorance, because we know a great deal, not certainty, because the decisive measurements have not been made. Disciplined uncertainty is harder to sell than a simple answer, but it is the only honest way to talk about a world that has spent 4 decades punishing simple answers. And perhaps that is why Uranus is such a good subject for a deeper account. It begins with an easy laugh and ends with a hard lesson. The universe is not obligated to align with our categories. A planet can look smooth and still be profound. A name can become a joke, while the object behind it becomes essential. A world can sit ignored in the far cold and still hold the key to a population of planets spread across the galaxy. There is another reason Uranus matters that is easy to overlook. It tests our instinct to rank scientific importance by visual spectacle. Jupiter announces its complexity with bands and storms. Saturn announces it with rings. Mars announces it with landscapes that look almost familiar. Uranus hides almost everything that makes it important. Its greatest structures are not visible to the eye. They are in its gravity field, its magnetic geometry, its heat budget, its high-pressure chemistry, and the orbital alignment of objects too small and dark to see without instruments. It is a reminder that the most important data in science are often not the prettiest data. This is especially true in planetary interiors, where direct observation is impossible. No spacecraft will drill into Uranus, no probe will reach the region where water, ammonia, and methane are compressed into exotic phases. The pressures would destroy any machine long before it reached the relevant depths. So planetary scientists must infer the unseen from the measurable. A small change in gravitational harmonics becomes a clue to mass distribution. A magnetic multipole becomes a clue to dynamo depth. An atmospheric abundance becomes a clue to formation location. A heat imbalance becomes a clue to convection. The planet is studied like a locked room, where every sound through the wall and every vibration in the floor must be interpreted. That method is powerful, but it requires many independent clues. One clue can mislead. A flyby can sample an unusual moment. A telescope can see only certain wavelengths. A model can fit one measurement while failing another. This is why Uranus has remained difficult. The clues we possess are real but sparse. They point toward a hidden structure, but not yet with the redundancy needed to settle the case. An orbiter changes that because it produces repeated constraints. It does not simply take a better photograph. It watches the same world from many angles and lets the planet's own rotation separate spatial structure from temporal variation. It can distinguish a magnetic feature tied to the planet from a disturbance caused by solar wind. It can detect whether atmospheric storms are rare accidents or parts of a seasonal cycle. It can measure how ring structure changes under gravitational forcing. It can fly past moons repeatedly and build geological maps rather than isolated portraits. The difference between a flyby and an orbiter is the difference between hearing one sentence of a language and living among its speakers long enough to understand grammar. There is also a consequence for planetary origins. Uranus and Neptune likely formed through a delicate race against the dispersal of the solar nebula. If their cores grew quickly enough, they could capture hydrogen and helium. If they grew too slowly, the gas was gone. Their final masses suggest they stopped short of becoming gas giants. That stopping point is not a failure. It is one of the most common outcomes in planet formation. But why did they stop where they did? Did they form where they are now, where growth is slow? Did they form closer in and migrate outward? Did the disk run out of gas? Did competition with Jupiter and Saturn starve them? These questions cannot be answered by theory alone. The composition of Uranus is a fossil of that race. Too much heavy material, too little hydrogen, unusual noble gas ratios, unexpected water enrichment, or a rockier interior than assumed would each point toward a different history. The planet's present structure is therefore not only a physical puzzle, but a historical document from the solar system's first few million years. That history may also explain the tilt. If a giant impact occurred, it likely happened during a time when large planetary embryos still moved through the outer solar system. If a resonance tilted Uranus, it likely required a specific migration pathway. If the moons formed after an impact, their compositions may record the mixture of target and impactor material. If they were carried through a slow tilt, their orbital histories may preserve a different signature. The tilt is therefore not just an odd angle. It is a timestamp, or at least an attempt at one. It asks when Uranus became Uranus. The answer matters because the early outer solar system shaped the inner solar system too. Migration of the giant planets scattered small bodies, reorganized reservoirs of comets and asteroids, and may have influenced impact rates on the rocky worlds. Understanding Uranus's formation and migration is not isolated from Earth's history. The architecture that placed Uranus on its current orbit helped shape the dynamical environment in which Earth, Mars, Venus, and the small body reservoirs evolved. A distant ice giant can carry clues about the conditions under which the inner planets stabilized. This is another reason the phrase local mystery is too small. Uranus sits far away, but its story is woven into the entire solar system. The same early gravitational rearrangements that may have tilted or moved it helped sculpt the Kuiper Belt, and perhaps altered the delivery of water and carbon-rich material inward. The same small bodies that became comets, the same migration patterns that captured resonances, the same instability that changed Neptune's orbit may all belong to the background of Uranus's present state. The planet is not a remote oddity. It is a surviving participant in the solar system's formation drama. And yet, for all that scale, the most moving part of the Uranus story may be its restraint. A world can be revolutionary without looking dramatic. It can carry evidence in numbers rather than images. It can reshape exoplanet science without ever being popular. Uranus teaches a kind of patience that modern astronomy badly needs, because we are entering an age where the number of known planets is growing faster than our ability to understand each one deeply. Catalogs can make worlds feel familiar too quickly. Uranus says, slow down. A radius is not an interior. A color is not a climate. A smooth disk is not a simple planet. If we let that lesson guide us, Uranus becomes more than a target. It becomes a warning against superficial certainty. The first era of exoplanet discovery taught us abundance. Planets are everywhere. The next era must teach us interpretation. What are those planets made of? How do they cool? What do their atmospheres hide? Which ones keep magnetic shields? Which ones lose their air? Which ones are layered, mixed, stripped, inflated, or chemically transformed? Uranus is one of the few places where those questions can be tested against a world close enough for direct investigation. So the final answer is not that Uranus alone will rewrite planet formation. The final answer is that Uranus gives planet formation a chance to correct itself. It offers a nearby case where theory, simulation, laboratory high-pressure physics, remote observation, and spacecraft measurement can meet. That convergence is rare. It is the kind of opportunity science should not leave unused. That is why the next chapter cannot be written from Earth alone. Telescopes can keep watching the changing clouds. Laboratories can keep squeezing water, methane, and ammonia into stranger phases. Simulations can keep testing impacts, resonances, and layered interiors. But at some point, the argument needs the one thing every real scientific controversy eventually needs: a new measurement that both sides must answer to. Uranus is not asking for belief. It is asking for an orbiter, a probe, a magnetometer, a gravity experiment, and time. A planet that has carried its secret for 4.5 billion years can wait a little longer. But our models cannot wait forever, because every distant sub-Neptune we discover is being interpreted through the uncertainty Uranus represents. The longer we postpone the return, the longer we keep using a key we know does not fully fit the lock. And that is the quiet pressure behind the whole story. We are not only trying to solve a distant planet, we are trying to learn how often our first explanations fail when they meet a world built from materials, impacts, and histories we have barely sampled. Uranus is close enough to correct us and strange enough to matter. That combination is rare. The planet is not broken. The planet is complete, Our explanation is what remains unfinished. The ending image is the same as the beginning, but now it should feel different. A pale blue-green world in the outer dark. It still looks calm. It still gives little away. It still turns on its side through an 84-year orbit, one pole lit for decades, one pole dark, its moons circling in a tilted plane, its magnetosphere twisting into a corkscrew as the solar wind presses against it. Somewhere below the clouds, water, ammonia, methane, rock, hydrogen, and pressure arrange themselves into layers we have not yet seen. Somewhere in that hidden interior, heat from the planet's birth is still trying to escape. Somewhere in a conducting shell, a magnetic engine is running in a geometry no textbook expected. Uranus is not waiting to entertain us. It is waiting to correct us, and that may be the most important role a planet can play. Not to fit the theory, but to force the theory to become large enough for reality. Because beyond the orbit of Uranus, beyond Neptune, beyond the Kuiper Belt, beyond the small icy bodies drifting in the dark, the galaxy is full of worlds in the same size range. Worlds with thick atmospheres, hidden interiors, strange dynamos, ambiguous compositions, and histories we cannot read from far away. We will not visit most of them. We may never know their names. But the physics that governs them may be waiting in the quietest-looking planet in our own solar system. A planet knocked sideways, perhaps. A planet insulated by exotic layers, perhaps. A planet shaped by impact, migration, chemistry, and time, almost certainly. A planet that refuses to be explained by one simple story. That refusal is not a failure. It is the signal. It tells us that the solar system is still not fully known. It tells us that the outer planets are not finished chapters. It tells us that the most common kind of world in the galaxy may be hiding behind the least explored kind of world at home. And it tells us that sometimes the universe does not announce its deepest lessons with fire, storms, or rings bright enough to see from a backyard telescope. Sometimes it teaches through a quiet blue planet, rolling sideways through the dark, holding its heat close, twisting its magnetic field through space, and waiting for us to stop laughing long enough to listen.